in butane. But there is a other possibilities. So there will be other possibilities like this way: CH3, CH. We can write here CH3 and followed by CH3. You can see your molecule have a how many? This is the CH3. This is CH3. CH3 means hydrogen will be 9 plus another hydrogen is 10 and carbon is 1, 2, 3, 4. So you can see the C4H10. This case also you can see the C4H10. So both the cases you can see the C4H10 is maintained, but first one we call it N-butane. Second one we call it, this compound we call it the isobutane. So basically what you observe that they are the same empirical formula in two cases, but their connectivity, the constitution is different. That's why it is called the chain isomerism. Okay. So next, if I give you another type of example, which is C5H12. So C5H12, the classic one will be CH3, CH2, 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 and CH3. This is called N-pentane. Okay. So there is a other structure like the previous one. If your position of the group is like this way, suppose CH3 and Baki CH2 and followed by CH3. So what do you see? This is number of carbon is same, but the position of the CH3 group or the carbon position is little bit changes. So the chain structure is changes. So this first one is called the N-pentane. First structure is called N-pentane. This structure is called isopentane. And there is another possibility is there. What is another possibility? If you consider this is like this, that will be this CH3, CH3, and 1, 2, 3, 4, and this is CH3. So this is called neopentane. So you can see the formula is all the cases. You can see the C5H12, but there is a three different. So all are the class of chain isomerism or the nuclear isomerism. Okay. So next I will discuss the another interesting one is the positional isomerism. Positional isomerism means if different compounds belongs to the same homologous series with same formula, same carbon, but different the position of the functional group. The functional group position will be changed now. For example, if I consider CH3, CH2, CH2, OH. This is called the normal 1-propanol. Okay, this is called 1-propanol. Okay, now we can write this OH group in a different position. For example, how can we write this? CH3, CH, OH, CH3. Okay, now what you observe, the OH position is now initially in the terminal position. Now OH position in the branch positions. So initially it's called 1-propanol, second one is called 2-propanol. So the positional isomer means the functional group position is changed. So that's why it is called 2-propanol. Why it is 1-propanol? The numbering will be like this: 1, 2, 3. Here the numbering is 1, 2, 3. This is coming from IUPAC nomenclature. Okay. So that this is the one example of the positional isomerism. So you can find out in our this study material, there is many more examples there. I'm not spending here more times in this particular topics. There's another interesting is the metamerism. What is metamerism? This is a special kind of structural isomerism in which different compound with same molecular formula belongs to same homologous series. Okay. For example, if I consider diethyl ether. Diethyl ether means this is CH3, CH2, O, CH2, CH3. Okay, so there is an analogous compound of this one will be methyl propyl ether. So here you can see this side is ethyl group is there, then oxygen, this is a ether linkage, then another ether group is there. Okay, now we can consider in a different way. How can we consider CH3, CH2, CH2, O, CH3? So like previously we call it diethyl ether, we can say the methyl propyl ether. Okay, so methyl propyl ether, that means both have a same empirical formula. Okay, but the constitution is little bit different. In special case, okay, the distribution of the alkyl groups around the central atom is different. So there you can get the different type of ketone compound also. So if you consider the another types, if I consider ethyl, CO, ethyl, we can draw this compound is called diethyl ketone. We can write this compound in a different way. For example, CH3, CO, propyl. I'm not writing anymore. Propyl means CH2, CH2, CH3. So this called methyl propyl ketone. So all are the example of metamerism. Okay. Now there is another interesting topic there, which is called the tautomerism. So compounds which has structure differ in the arrangement of atoms, but which exist simultaneously in a dynamic equilibrium. Means what is the meaning of this? For example, you consider a molecules. That molecule can exist in two different forms at a time in a equilibrium stage. So that particular case we call it the tautomer of one each other. For example, if you consider ethyl acetoacetate, CH3, CO, CH2, CO, OET. So this is called the ethyl. The term is coming from ethyl. This is called the acetoacetate. So you can see these cases, ester group you can see it and the ketone group you can see. But there is a possibility for this hydrogen. There is a two hydrogen is there. We can consider there is another hydrogen. We can write it like this way: CH and hydrogen. That hydrogen can tautomer like this way. So then there is a possibility of the structure will be CH3, C, double bond C, H, CO, OET, and OH. So initially you observe this is a ketone group. It's a ketone. Okay. Now what you observe? This is a enol group. So ketone and the enol, they are staying together in a equilibrium, and there should be a driving force in particular cases. So that is not important in because it's a little bit deeper. The driving force will be when it will be make this such kind of OH, they will make a hydrogen bonding with this ester group and they are stabilized by this way. Okay, so that is the driving force for preparation of such kind of cases, the OH group. So this is the enolic form of the ethyl acetoacetate. So this keto one tautomer in the form of enolic one. Okay, so this is there is a lot of examples are there. Okay, so basically whatever I have told you in the from the beginning, so all isomerism, this is related to the structural point of view. So all of the structural isomerism. So structural isomerism is a very few because it's only the connectivity or sometimes the position is changed or chain position is little bit different. But the important one is the another interesting one is the stereoisomerism. So stereoisomerism, the term I will discuss in details because stereoisomerism is content stereo. The term stereo coming, it's actually because of the when you try to draw a particular molecule in a 3D orientation in three-dimensional way, then the stereo, the terminology will become in the three stereo. Okay, so in stereoisomerism, there is a different categories. First one is the geometrical one, geometrical isomer. The another important one is the optical isomer. Number 3 will be conformational isomer. So what I'm saying, whatever I have explained today, the up to the initial one, the structural one, is not so much important. The biggest important section is the stereoisomerism. So when you will explain the stereoisomerism, the first will come the geometrical isomer. So geometrical isomers have a lot of different conditions. When a particular isomer, we call it's a geometrical isomers. Okay, the molecule must contain a one carbon-carbon double bond, which there is no free orientations or free rotations. So that means geometrical isomer will be generated. That means your molecule should have a double bond. Okay, so double bond is mandatory. At least one should be mandatory. This is the first criteria. Second one is each of the double bonded carbon must be attached with the two different functional groups. That means geometrical isomers, the simplest molecule all of you know in the double bond will be the ethylene. Am I right? Ethylene does not means all the substitution are same, but this molecule will not generate any kind of geometrical isomerism. So when it will be generate geometrical isomerism, the condition should be either AA, BB, okay, or it should be like this AB, AB. So if you see, sorry, I'm written wrong. This is AB, AB. If you get AB like this way, then this one, your substitution is different. You see AB, but this connectivity in a particular carbon, you can see the two substituents are same. So this one will not generate, will not give you the geometrical isomerism. This one will not give you the geometrical isomerism. Only this one will give you the geometrical isomerism. Clear? So the basic condition is that when you consider the substitution on a particular carbon, the first condition will be double bond should be there. Second one is in a particular carbon, the two substituents should be different. Two substituents will be different. Okay, this is the point number 2. So next, let's talk the real example. Okay, so if I consider methyl hydrogen, methyl hydrogen. Okay, so with respect to this double bond, you can see the two with respect to this double bond. If I consider this is a double bond, you can see the two methyl are in the one side. So then we call it a cis isomer. Okay, if with respect to the double bond, if the methyl substitutions are in the opposite side, then we call it trans isomer. So these cis and trans have another interesting name, which is called it cis is called J, trans is called E. Okay, so this is very important when I'll discuss in future for a lot of different type of stereochemical compounds. This is very much important to understand about this kind of points. So now I have written the 2-methyl and 2-hydrogen. So you can do lot of different type of substituent. For example, another substituent I'm going to explain. This is CO2H, CO2H, hydrogen and hydrogen. So here you can see 2 CO2H again in the same side. So here another important point is when the connectivity is there. For example, this carbon is connected with the two different substituents. You give the priority. Which group will get the priority? Here definitely CO2H group will get the highest priority. I will explain from which angle you can explain the priority. Okay, in little later, and then the hydrogen will be acid group is the highest priority, then the hydrogens. So that's why I can write this is 1, this is 2. Again, this is 1, this is 2. So when the two priority group are in the same side, we call it cis. When two priority group in the opposite side, we call it trans. When it is cis, we call it also jet. When it will be like this way, we call it trans or E. Okay, this or clear. So basically, what you observed here, this case, this is a 2D representation of a molecule. There is no 3D representation we can do. Okay, because this is a sp2 carbon, this is also sp2 carbon. So you can have 2D representations. But if you consider a 3D molecule, for example, sp3 carbon, carbon which is substituted with and D. 4 different substituents. Not necessarily always 4 different. I mean, that may be in the same substituent is also there. Okay. So that means this molecule is 3D 360 degree, 3D 360 degree. Sorry, not a 360 degree. Better not to write 360 is not a correct word to say like this way. Okay. So what you observe here, the stereochemistry will for such kind of molecules, if you try to explain, then you need lot of other factors to explain such kind of molecules. Okay. So basically, if you try to know the stereochemistry of these molecules, there is a lot of other terminology will be arrived. So one should be called lot of term will be there. I will explain one by one. Chirality, optical isomerism, conformational isomerism. So first, when a molecule we call it a chiral. When which condition we can say it's a molecule is chiral. The first criteria should be, I have drawn previous slide A. I have drawn another molecules is A, B, C, D. Okay. If all the substituent is same, if all the substituent is A, then this molecule should not be chiral. Number one. Number two, if three substituent is same, one substituent is different, then this molecule also not chiral. Number three, if two substituent is same and other two substituents are also not same, then that molecule also not chiral. The chirality means the criteria should be all the substituents should be different. So only that particular cases you can generate the chirality inside the molecule. This is the basic criteria. And that will also give you the optical isomer. I will explain later. So this is the basic criteria. Okay. So in your syllabus, the major portion is there. I will explain first that, then I will go to the other sections. Okay. For example, if I consider, I think all of you studied this one. Or it is written deuterium. So this is the called Fisher projection formula. Am I right? So this is the Fisher projection formula of a particular molecule. So this molecule is chiral or not? Definitely this molecule is chiral. Why? Because all the substituent is different. Ethyl, hydrogen, deuterium, and methyl. Okay, so that means this molecule should be have a distinct chirality in this particular one. Okay. Number one. Number two, which kind of chirality is there? Is it R or R and S? R and S means the term is R and S. All of you studied little bit in the 12th level. R and S, the optical rotation, when you are giving the numbering of your priority of the groups, which is coming from a theory is called Kahn-Ingold Relox rule, okay, which is called the CIP rules. From there we can find out the real numberings and other. The first condition will be rank atom attached to the chiral centers according to their atomic numbers. So highest the atomic number, it will get the priority. Okay, highest the atomic number means if I consider any cases, bromine will be get the priority, then chloride, then fluoride. Okay, and iodide will be सबसे ज़्यादा priority मिलने वाला है. Iodide will be highest priority than the hydrogen. So this is the one. When the atomic number is different, then that cases you have to consider the mass number also. Mass number if I consider means ethyl will be get the priority, then the methyl one. Okay. So suppose hydrogen and deuterium is there. Okay, two isotopes are there. That cases deuterium will be get the priority than the hydrogen. But definitely, if you consider the series here, okay, definitely ethyl will be more priority than the methyl, then the deuterium, then the hydrogen. Clear? So this is the number one criteria. So then you have to give the numbering 1. This is 1. This is 2. This is 3. This is 4. Because as per our CIP priority. Okay. So now you have to rotate from 1 to 2 to 3. So 1 to 2 to 3 is that directions. The rotation will be that directions. So it is a clockwise rotation. Am I right? So in the clockwise rotations, if there fourth number of group, the which one is the fourth? Hydrogen is the fourth. Fourth, if it is a vertical positions, then it should be the reverse one. Reverse one means if it is a clockwise rotation is R, anti-clockwise rotation is S. But if your fourth number group in the vertical position, then it will be reverse. So here you can see this, it's looking like R, but originally it will be S. Clear? I am going to explain another example. so that you can get better understanding. Methyl, ethyl, deuterium, and hydrogen. Just I have changed previously. You can see the just I've changed the position of the hydrogen and deuterium. Again, I am giving the numbering. This is 1, this is 2, this is 3, this is 4. So as per your rule, it will be rotated like this way. This is anti-clockwise, but hydrogen again in the vertical position, so it will be R. So generally it will be looking like a S, but it will be R. Okay. So this is the first priority of a CIP rule. Sometimes this theory is also have a limitations. Atomic number, atomic mass number, there is some limitation. Then you have to go the next theory. What is the next? For example, if you consider a molecule looking like a substitution like CHO, CH2OH, and another substitution is there, CH3 and CH2 deuterium. So how can you give the priority of this group here? So if you try to give the priority, the first rule is, so this center, this if you consider only one chiral center is there in this molecule, and the substituent is, if I consider this is a, this is a B, this is a C, this is a D. As per I have already explained previously, A does not equal to B, not equal to C, not equal to D. So this is the first criteria. Okay. So then that means this center will be chiral. Okay. Now you consider the numbering. Which group will be the priority? Here, little bit complex, not so much easy. So which group will be? So definitely CHO, definitely CHO and CH2OH will have a priority than the methyl and deuterium compound. Clear? Because that contain oxygen, that contain only hydrogen and deuterium. Now, in between this CHO and CH2H, which one will get the priority? You can see CHO means carbonyl hydrogen. Okay, that one we can break it like this way: carbon, oxygen, carbon, oxygen, and hydrogen. Okay. In the case of CH2OH, we can write directly CH2OH. There is no any other group is there. So that means if you consider here, you can see hydrogen is there. Here you can consider this is also hydrogen, this is also hydrogen. Forget about this. So this is common. Okay. Next, this is you are getting oxygen. Here you are getting oxygen. Next, here you are getting hydrogen. Here you are getting another oxygen. Okay. So that means that indicates that aldehyde have a higher priority than the CH2H. So aldehyde have a higher priority than the CH2H. Okay. Next, if you consider the methyl and the deuterium, two hydrogen is there, but here deuterium is there. So this is the priority. So now if I say the numbering here, CHO will be 1, CH2OH will be 2, CH2 deuterium will be 3, and methyl will be 4. So 1, okay, okay. So now if you see properly, this is the 1, this is 2, this is 1, Okay, there is some problem in this page. Deepak. राइट नहीं कर पा रहा हूँ। ओके ओके कर दीजिए, आप डिलीट कर दीजिए, मैं दोबारा लिख देता हूँ। छोड़ दीजिए इसको, छोड़ दीजिए नेक्स्ट पेज में दे देता हूँ। Leave it. Okay, so this is the molecule. So this is the molecule I have drawn here: CHO, CH2OH, and I did not remember. Oh, forget about that. CH3 and CH2 deuterium. Okay, just I have, if you forget about the previous one because I did not, because that's deleted, so I did not remember. Okay, so I have already told this is the priority number 1. So this is a priority number 2. That will be priority number 3. That will be priority number 4. I have already explained in the last one. So now your rotation will be looking like, sorry. So your rotation will be 1, 2, and looking like this way. 1, 2, 3. And so it is rotated clockwise, but this CH3 in the vertical position. Fourth number group, the number 4th group in the vertical one. So as a result, it will be, instead of R, it will be S. Clear? So this is very important for any kind of structural analysis of any molecule. Okay. So there another important structure. This is the, I have explained all the example I have explained in the only one particular center. So there is another possibility. If more than one center is there. Let's talk about some interesting example. CO2H, H, OH, OH, H. Okay. So that means you can see this is the connectivity of this chiral center, have 4 different substituent. OH is different, CO2H, OH, and CO2H. This center is also different. Now if I give the numbering of this particular center, again OH get your first priority, then acid group your second priority, and this group will get the priority number 3, and this group will be 4. With respect to this one, the center number 1. Now if it is a 3, this is 2, it is rotated in a anti-clockwise, but 4th number of group in the horizontal line. Okay, so it is in the horizontal line, so as a result it will be, instead of S, it will be R. Okay, similarly OH, here 1, this is 2, and this all the full section will be 3, and this is 4. So again, with respect to this particular center, it is rotated like this way. Okay, so it is, if it is rotated like this way, that means again it will be anti-clockwise. That means it will be again S, but this hydrogen again in the horizontal line. So that means it will be the, instead of the S, it will be again R. Okay. So I have already explained this only with respect to one particular example. Come back to this case. Now, if you put a mirror here, what you observe? This CH3 is here. This CH2 deuterium will be here. This CH position not be changed. So this CH2OH will be here. So what you observed for this molecule is S. So definitely this should be R. And the relationship between this molecule A and molecule B is called enantiomer. When there is a mirror image relationship, this is called the mirror image. I have put a mirror here. When you see the mirror image relationship, that case you can call it such kind of case. It will be a enantiomer. Okay. For example, here, if you put a mirror here, what you observe? OH here, hydrogen here, OH here, hydrogen is here, CO2H group is here, and that CO2H group will not be the position change. So that center is R, definitely that will be S. That center is R, that will be definitely that will be S. So again, if I consider this a molecule A and molecule B, the relationship will be again enantiomer. Enantiomer means the two compound will be their mirror image to each other. Okay, and definitely previously I have explained only one chiral center. Here you can see both the cases you have two chiral centers. Clear? So two chiral centers still in this molecule will be enantiomer. There is a very interesting example I am explaining you. Let's consider OH, OH, hydrogen, hydrogen, CO2H, CO2H. See, previously what you observed, this center is R. Okay, definitely this that will be also R, and definitely that will be S. So now you can see this center is R, this center is S, but this compound is called mesomer because these molecules have a half of the molecule is mirror image to the half of the molecule. As a result, the overall molecules have a no chirality. There is this molecule have a overall molecule have a no chirality. There is no optical rotation for this molecule. Clear? So as a result, this molecule is called the meso compound. Okay. So this is a very interesting example I have explained. And whatever I have drawn till now in all the example is the Fisher projection formula. This is the one particular one is the Fisher projection formula. Now let's talk about to draw in a different way. Suppose let's talk the last one H, OH, H, OH, CO2H, CO2H. So this is a Fisher projection formula. Okay. Now, if I try to say to draw this molecule in a Sohor's projection formula, okay. So there is a lot of technique is there. Whatever I will teach you, just follow my techniques. You can solve any problems in the stereochemistry. Okay. So my vision in this molecule from that because I am observing the molecule from that particular direction. So that means this carbon center will be my front. I'm drawing this carbon skeleton like this way. So this is my eye is from here. So I'm the visualizing the molecule from that particular place. Okay. So what I observed from here, you can see that will be my left side. Left side is hydrogen, right side is OH. This one is the left side hydrogen, this one is the right side OH, and this one is CO2H. Similarly, if I observe from that direction, again that particular carbons, left side is hydrogen, right side is OH, left side is hydrogen, right side is OH, and this CO2H group is down. So this structure is called Sohor's projection formula, and this is a eclipsed form. This is a eclipsed conformation. Why the term is conformations? Conformation means I have drawn a molecule. So you see, Fisher projection formula is a 2D formula. Sohor's projection formula is a 3D formula. 3D means you can draw a molecules in a 360 degree in a different angle. Suppose I am rotating a molecule only 0.1 degree. You can rotate the molecule 5 degree. Some other people came and draw the rotate in a 120 degree, 140 degree, 260 degree. Many more rotation is possible. When you rotate the molecule, you will get a new structure, new conformations. Another people rotate the molecule, they get the new conformations. So that means in a particular rotation, there are a lot of different conformation will be generated. So that different angle will different conformations. So one molecule have a lot of conformations. But for example, this case, the conformational angle is 0. Eclipse means 0 degree. So means all are stacked with each other. Clear? So this case, conformational angle is 0. And molecule always try to stay in the most stable configurations. So if I say Sohor's projection formula, which one will be your stable configurations? I'll show you again. So I have drawn here. You can see in the previous slide, I have drawn H, OH, CO2H, H, OH, CO2H. From where I got this? I got from the Fischer projection formula. I have told this is a eclipse structure. Now I rotate, and this is the eclipse and the highly unstable one. Highly because they are facing to each other. They are facing, these OH are facing from each other. Okay. The most stable will be if you rotate the molecule 180 degree. And what you will observe, I am fixing this one because my eye is from here. I am fixing this carbon. So H, OH, CO2, H will be fixed. I am rotating the back carbon 180 degree. When I'm rotating the back carbon 180 degree, CO2 OH down method, that will be going up. That OH also coming here, and that hydrogen is coming here. Clear? So this is the another structure. In general, this is the more stable, but this is a particular case. This case will be not. This is the more stable. There's another possibilities are there. I will explain later. Okay. Now, if I try to say convert from here to the Newman projection formula. So this is another projection formula. How can you convert? So what I do? I put my eye from here. Newman projection formula. You have to draw a circle first. Then your eyes is here. Okay. So this carbon you are visualizing first. So that will be your front carbon. Okay. H, OH, CO2H. Clear? So which carbon is the back? That one. So I can write like this way: H, OH, and CO2H. So this is the eclipse structure of the Newman projection formula. So if here I have 180 degree rotated the molecule. If I rotate the molecule here also 180 degree, what we will observe? 180 degree rotation में आपको क्या मिलेगा इधर? So again I am fixing the top one because I am visualizing the molecule from here. So I am fixing here this one H, OH, CO2H. Then I am rotating. So this is the staggered configurations. This is called staggered conformations. This staggered conformation will be more stable because they are making a hydrogen bonding with the acid with the OH. Here also from these structures. Clear? So next few slides I will explain more example because this is a very interesting date. From here a lot of question arrived in your exam also. Let's consider this one. CH3 H Cl Cl H CH3. Okay, so this is the one is called the Fischer projection formula. This is a Fischer projection formula. Clear? Now, if I told you to draw the Sohor's projection formula, again my theory is my eye is here. I'm visualizing the molecule from that direction. So I'll draw the first skeleton. My skeleton will be looking like this. And you can see the chloride is left side. Chloride is left side. Hydrogen is the right side. Methyl in the down. Clear? The next carbon is hydrogen is the left side. Chloride in the right side. CH3 is the down. So this is the classic one. Next, this is called the Sawhorse projection formula. Now, if I draw from here to the Newman one, again my eyes is here. You can directly draw from here to Newman also. There is no issue. If I directly draw from here also, you will get the same thing. My eyes is particular that carbons. So this is I have considered chloride, hydrogen in the right, methyl is the down, and that carbon the behind the one I have drawn like this way. Not complete line आपको draw करने के लिए जरूरत नहीं. You no need to draw the full line. Only the short line you can draw. Hydrogen, and this is will be the chloride, and the methyl will be down. Now another interesting point. You can see all the connectivity is 120-degree angle. This is a 120. This is a 120-degree angle. Okay. So always you have to maintain that one also 120 degree, that one also 120 degree, and that one also 120 degree. You have to maintain. No, don't put this. Don't put this kind of two short line in one particular sites. Okay. For example, what I'm going to say, if you draw hydrogen, sorry, you draw chloride, hydrogen, methyl, and the picture what is there, hydrogen and methyl and chloride. This is wrong because you can't write like this way. Okay, means two groups you can't put in a one particular size, because then the angle will be lower, less than 120 degrees, then this angle will be more than 120 degrees. Okay, so that will be completely wrong. So then I'm going to teach you from here that another very interesting one. All of you study the flying wedge formula. There is another interesting one, is the flying wedge formula. For example, you can say CH3, HCl, Cl, CH3. That molecule I'll draw again. So CH3, 8 Cl, Cl, 8 CH3. So this is a Fischer projection formula. From here, I can draw another new projection formula in a three-dimensional way, flying wedge. How can I draw this? What I'll do, when I move that molecule, when I move this methyl group in that particular direction, that whatever the group will be there, that will be shifted, that will be moving to up. When I methyl group moving to that particular direction, whatever group will be there, that group will be shifted to up. So let's talk about that. I'm moving like this way. So which group I am moving? The methyl group. Which group I am moving? The methyl group. So that case, I'm considering this one is this one, this carbon. Okay. So then chloride will be up. Up means you have to draw like this way. This is a wedge formula. Chloride will be up. Definitely hydrogen will be down. Here also chloride will be up. Hydrogen will be down. Okay. The important point, whatever stereochemistry is there, that is written, means that is actually preserved in these molecules, written in your molecules. Okay. So whatever the stereochemistry is there, for example, chirality is there, chloride is 1. This full group will be, this full group will be with respect to that center 2, that will be 3, that will be 4. So it will be rotated, it will be rotated. 1 minute. It will be rotated like this way. 1, 2, 3. So that means it will be rotated. Oh, sorry. So it will be rotated like this way. So that means it is a clockwise rotation. But hydrogen in the 4th ranking group in the horizontal lines. So it will be, instead of R, it will be S. Similarly, again, if you consider from that perspective, So I am changing the color. This is a 1. This whole group will be 2. This is 3. This is 4. Okay. Now it is rotated like this way. Sorry, 1 to 2 to 3 like this way. Okay, 1 to 2 and like this way. So that means it is rotate again clockwise. Okay, but hydrogen in this position, so it will be again S. So what you are getting S and S. That means this center also S and S. It will be returned. Okay, in your final in that particular cases. So this is a very interesting point. Now, if I given a molecule, then if I told you to convert from flying wedge formula to the Fischer projection formula. Let's talk about some interesting molecule. Suppose here methyl, here chloride. This is hydrogen. This is deuterium. This is hydrogen. This is deuterium. Okay. Now this is a flying wedge formula. If I told to draw this molecule in a Fischer projection formula. Okay. So I am observing my molecule from that particular direction. That means this carbon will be down and that particular carbon will be up. Okay. So I am drawing this a Fischer projection formula. So I am moving this methyl group to that particular direction because you have to make a line. Okay. You have to make a line. So your methyl is coming here. So I have told whatever group in the up that will be shifted to the reverse direction. So which group is there? Deuterium is there. Deuterium will be shifted to the left side. Definitely hydrogen will be coming here. And this case chloride you are moving from that direction. That means chloride will be going up because it's a straight line. Which one will be moving? Hydrogen. Hydrogen will be moving to the right. And deuterium is here. You can try by yourself. Whatever I have told you, you can try by yourself. You will get the same result. Now you can have a different substitution is there. You can make a numbering on that particular one. So this is a flying wedge formula. This is a Fischer projection formula. Okay. Now if I told you to draw for this molecule Sauer's projection formula, how can you draw this? Okay. So if I told you to draw a Sauer's projection formula for this molecule, then your eye will be again from here. So what you observe? Deuterium is here, hydrogen is here, methyl is here. Clear? Because deuterium in the left side, hydrogen in the right side, and methyl in the down. From that perspective, deuterium again in the left side, hydrogen in the right side, and chloride in the down. Clear? So now what I have drawn? This is Sauer's projection formula. This is a Sauer's projection formula. Now, if I told you to draw a Newman projection formula from here, you can draw it again. Okay. So this carbon is again my first carbon, deuterium, hydrogen, and methyl. Clear? The back carbon, what you observe, deuterium, hydrogen, and chloride is there. So that one also we can draw like this way. This is a deuterium. I have already told you last time, you can't draw the same phase, and this case will be your chloride. Sorry. That should be your chloride. So this is your Newman projection. So that means I can convert from flying wedge to Fischer projection to Sauer's to Newman. Even I can convert in the reverse way, Newman to Fischer to Sauer's to flying wedge. Okay. If you try to consider any molecules, you can convert from one structure to the other one. That's a very interesting concept in the stereochemistry. If you understand only one particular types, you can explain everything. Clear? So this is This is the, so today I'm going to actually try to ending you here only. Next class, tomorrow I will start from here and I will finish the stereochemistry. Then I will start the nucleophilic substitution and the elimination reactions. Okay. If you have any kind of queries regarding any kind of structures and any problems, you can write in the team and I'll try to solve the problems in the next class. Okay. So that's all.